So this is not a field I know a great deal about. I sort of got interested in this from having to referee some papers, which have sort of forced me to try to understand them and understand what this is all about. And I sort of find the computer science papers a bit better written and easier to understand. I mean, so that would be my recommendation for, you know, to someone wanting to learn this, if you want to learn this. And I also have some references. I also have the feeling that the successes are much greater with image processing, with you know, non-astronomical problems, but this is just sort of an impression. So I'll show you some things at the end that sort of personally impress me. I guess I sort of wanted to start with just saying a few words about computer programming. And so I think, you know, most computer programming is sort of super micromanaged, and, you know, I mean, maybe not at any moment, but you have a sort of super precise idea of what you want your code to do, what the input is, what the output is, what are the algorithms, etc. And a lot of the art of computer programming, as we learned it, is to sort of, you know, not make mistakes. One little bug will completely screw your code. And I just sort of listed some of these books. So the first two books are sort of more computer science books about algorithms and, you know, traditional programming would be, if we want to take a difficult task, how would you write a Linux kernel? How would you write a compiler? And things like that. And then I guess for us, a lot of what we do would be in, you know, numerical recipes, which is much the same in style. Someone told me that Numerical Recipes is the most sold book by Cambridge University Press, next to the King James Bible, which I find kind of amusing. Okay, so let's go to sort of neural networks. And, you know, this has a really long history. So, and I just made a list of references. This is by no means complete, but early on, there was a lot of thought about can you make computers do tasks that are sort of typically human tasks. And this perceptron, which means a number of different things in the literature. So I found sort of contradictory usages of this term, but it's sort of based on modeling the brain, and there's a lot of discussion about that. The second book is sort of very mathematical. So a lot of the things that we'll talk about here are not that new ideas, but the sort of success for this neural networks, deep networks, or whatever, is rather recent, that they've been able to do useful things. And a lot of that is due to just a lot of computing power, which wasn't around before. And then another tendency has been to sort of forget about trying to understand how the brain works. So if you look at this Goodfellow book, he sort of says, well, this is really old and people were trying to do biology, but we don't care about that, or the biological realism. We just want to make something useful. So that's sort of a bit of the history. And if you do want to learn this subject, I found this this course, the Stanford Computer Science course, really good. So the things that I like about it is that it has, it looks at a single problem, the classification problem, and it sort of goes through all the details in a simple way. It also has assignments and things about programming. And even though I haven't done this yet, I think, well, I do intend to do that, try to run some of these examples myself, but I think you really need to sort of do it. This is largely an empirical subject. The second book is a little older, learning from data, and it's not so much about neural networks itself. I think it's a bit mathematical and more theoretical and profound. And then the Ian Goodfellow book is rather simple and practical, and also complete. So this is sort of my impression of the good references on the subject. Okay, let's go to, we're going to leave biology rather fast, but I think it is useful to look a bit about the origins or inspiration of this field. So this is a nerve cell, and what basically happens is that there are all these different branches that are hooked up to other nerve cells that can create an excitation. And then an electrical impulse travels when the nerve cell is excited over the entire cell. And then it's hooked up to other nerve cells here through these synaptic terminals. So these are sort of the connections. And we'll see that the nature of these connections is sort of the thing that you vary and program. So I don't know that much about this, but I think the idea is that somehow these connections get reprogrammed, as a process of a human being or an animal learning. And but it's sort of the connectivity that, gives you the intelligence or function. The time scale is also very different. The nerve cells aren't very fast. So if you would consider one clock step, from one cell exciting the next, etc. I mean, they're not synchronized. It would be very, very slow compared to computers. So that's a bit of a clue. And then parallelism, that there's, that there isn't really any grand program. They're all doing their own thing. So that's sort of a bit the biological inspiration, although we'll see that it gets forgotten a bit. I'll also just say a bit about how these, what one sees in the nerve cell. So basically, there's a voltage between the inside and the outside of the nerve cell membrane. And there's a lot of, this is true for all cells. In the inside, there's a lot of potassium and almost no sodium, and a lot of sodium on the outside and very little on the inside. So you can sort of think of that as out of equilibrium. And they're kind of like batteries that are in opposite directions. And what happens is that if part of the membrane goes over this threshold, then the sodium valve opens up and you get this sort of action potential. So it sort of reverses or depolarizes in the jargon. And then the valve only stays open for a certain amount of time. And then the potassium valve opens up and it goes back. And then there's sort of this dead period. And then that it sort of spreads to the next part on the wall. So you have a pulse, and it goes everywhere in the nerve cell. So there's this action potential, and it's sort of an event that's either all or nothing. And these can repeat quite fast. So that's sort of the electrical theory behind it. And then there are these connections. So I'm going to sort of leave biology now and go to mathematics. So I think this is, this is an abstract neural network. And when we look at some of the more effective algorithms for looking at images, there will be sort of special purpose connections that allow you to do interesting things better with smaller networks. But let's just describe the general network. So you have these inputs, and you can think of this as a real number within, a certain range, say -1 to +1, or it doesn't have to be, very sharply defined. And then these connections here are the sort of edges in this graph connect to the next layer. So here you can see that everything is connected to everything else. And I'll describe in the next transparency mathematically what this connection is. And then you have a number of hidden layers, and then you have your output layer. So this isn't, I mean, this is generic, but it's actually quite specific and quite different from most computer programming. So in your graph, you know, the nodes to the left affect the nodes to only the next layer to the right. So there's no feedback. And so you would call this a feed-forward network. So, I mean, in electrical engineering, there are all sorts of fascinating things that can be done with feeding back the outputs into the inputs. And that probably happens in the brain, but people just chose to study this because this is complicated enough to understand, and there are interesting things that you can do with it. Also here, there's no timer or no clock cycle. I mean, this is just all one step. So you put your inputs here and you get your outputs. So this can be described as you have your outputs that depend on your inputs, and F is a nonlinear function. So there's no biological reality. I mean, it's just inspiration well, also there's no conditionals here. There are no ifs. So if you would think of writing a program where you can only have one step and no loops or anything, I mean, you would really be in a straitjacket. It wouldn't seem that you can do anything interesting with this. Okay, let's go to the mathematical description of what this function is. So, I mean, on the last transparency, I just said, well, it was a nonlinear function between the inputs, so that would be R, you know, the real numbers to the number of inputs to the number of outputs. So it's not as, it's a rather specific type of function. So here we have the layers are labeled by this index I here, and this is the rule for going from one layer to the next layer. So this is just a matrix. This is the weights. And then this is going to be a fixed nonlinear function. If it were a linear function, then we could just do a bunch of matrix algebra and we would just get one matrix, and all the intermediate layers would be completely irrelevant, or they wouldn't be doing anything interesting. Okay, so that sort of proves that this F, I guess it's called an action function from the, you know, action potential. That experience has shown that it doesn't really matter so much what function you have. So the sigmoid gives 0 for, you know, t if the input is negative, and then it sort of smoothly goes to 1. This is probably closest to biological reality, or and the hyperbolic tangent is sort of similar, but just shifted by a bit. and then it turns out that the computer scientists today like this sort of linear function, so that if it's positive, it doesn't do anything, but if it's negative, it just cuts it off. And this is very easy to compute because you just look at the sign bit, and if the sign bit is negative, then you just set the value to 0. So this is easy to compute and easy to take gradients of. And I think that's why it's used. You can prove theorems that any nonlinear function can be represented by such a neural network. So, I mean, that is sort of interesting. That shows that it's general. But, I mean, it's not just representing data. It's sort of the networks are used to extrapolate. So there's more to it than that. But that's something that the more mathematical types can prove and prove theorems about. So what would we want to do? So rather than, well, there are lots of things you can do with this, these networks. And, but one problem that has been studied a lot has been the classification problem. So you have these images, and this is from the Stanford course. So there are these photographs, and they contain either a car, a truck, an airplane, ship, or horse, or you could have some other combination. And I mean, the way you program this is you want to find weights so that the function does what you want it to do. So here we had these outputs, and the inputs would just be the, if it were a black and white image, just one input for each pixel. And then for each class, you know, car, truck, horse, you would want an output. But I mean, one way to do this is to come up with a probability distribution. So if you look at this function defined on the bottom, this takes outputs that are arbitrary real numbers and converts them into probabilities that add up to 1. And the idea would be that you would have this collection of objects, so you can find these on the web now. And then you would use part of the collection of objects to sort of program or train your network. And then with the rest of them, you would test it and see how well the extrapolation is doing. So this is a bit where the magic comes into it, and the theory is a bit lacking, because I'll explain to you what the program is to choose these weights. But on the part of the programmer, there's no intelligent design. There's no thought about how you would analyze these different objects. It's just done through choosing these weights through an algorithm. So this is where the jargon learning from data comes. So you can see certain problems. You know, your object is 3-dimensional. It could be, be seen from all sorts of different orientations. The lighting can be different, the colors, etc. So if we would want to sort of make a program where we would define what a car is or what a horse is, well, we would be able to, you know, a little kid would be able to answer the question and do very well at this exercise, but we would be a bit stuck and we probably couldn't write a good program. Okay, I'll go back to this. This is these special networks that look for patterns. But let's just sort of define this problem so that we can, you know, sketch how we would do this optimization. So we have these matrices W that take you from one layer to the next, and the F creates a nonlinear aspect of this, and then depending on how many layers you have, the nonlinearity appears at several places, and it can be shown that an arbitrary function can be represented in this way. That is with enough internal nodes. Now, the training set would be, this doesn't belong here, pairs of images. So this should be an I guess the boldface doesn't show well on the Beamer fonts. And then this is a lowercase l, which is the label. So this would have whether it's a car, a truck, a horse, or whatever, and then you have the pixels. So if we would want to make a sort of contest between different people's classification functions or their trained neural networks, we would want to define a loss function, which is basically, it would be equal to 0 if the network does a perfect job, and then there's a penalty for getting a wrong answer. So you take your sum over the training set, and then if the probability assigned to the right answer is 1, then this log is 0. And if it's 0 for everything, then this loss function is 0. On the other hand, if the right answer is assigned to 0 probability, there's a huge penalty for that. And I mean, you could argue, is this a good loss function? If someone bets 0 probability on something and they're wrong, then, you know, there's an infinite penalty. But anyway, this is all a function of the weights. So this defines an optimization problem that can be sort of solved in the usual way. So now we're going a bit into, you know, standard computer programming. So there would be loops over the different images, and then there would be a way of changing the weights. And for different problems, you would choose the loss function differently. But I just want to go through this classification. Okay, so we sort of agreed that we want to minimize a function. And this is the part that surprised me quite a bit, because I would have thought that this would be an impossible problem. So people who have, like in the CMB, done MCMC, you know, starting your chain and finding a minimum is, it takes quite a while and a lot of tries. In your standard minimization problem, apart from the problem of there possibly being multiple local minima and all of that, you tend to get flat directions, and the sort of gradient algorithm wouldn't work very well. So there are all these, I won't go into it, conjugate gradient type algorithms, things that compute higher derivatives. But if you have millions of parameters, you wouldn't be able to do this. So this is super simplistic. And then they put a hyperparameter, which is sort of how far down you flow with each step. And this works well enough. So this is somewhat surprising. And there are, I guess, a number of comments about why it works. Well, first of all, if the steepness were about the same in all directions, and there weren't these flat directions, optimization would be easy, independent of the dimension. The other thing is that in terms of programming these networks, you don't have to get the absolute minimum. And I don't even know whether it's necessary to get that close to the minimum. So this works if you hadn't, if one would, I think, sort of look, well, should this algorithm work? Well, maybe not, maybe probably not, if one is sort of pessimistic, but it sort of does. So this is how it works. So this is the stochastic optimization. And in fact, rather than doing a loop over all of the images, what is often done is a subset is done, and it's sort of stochastic. And that might even get you out of shallow false minima. So that could have some sort of unintended good consequences. The other thing is that there's this sort of trick. It's to compute the gradients. Here they have a sort of a tree with the different operations. And let's see, the green is the input values, and then you run this forward. This is just an example that your neural network could be represented as a tree with you know, the different additions and the multiplications and the nonlinear functions. So you go to the end, and then you put a 1 here, and then you compute the derivatives going back, and then the derivative, the derivative of the plus adds, you know, times 1. and by sort of following this tree backwards, you got the gradient. So this is sort of one of the, in these libraries, one of these standard things that is backpropagated, so you can figure out these gradients so you know where to move with optimization. There's also, I left it out, but generally in the loss function, you add some other parameter times, you know, the sum of all of the weights, because you don't want them to sort of get out of, to get too large. So that's just sort of a practical consideration. So this is sort of how to do this, a sketch, how to do this classification problem with generic neural network, where you have all everything connected to everything else. So here you have, if you have something that's say 20 pixels by 20 pixels, so you can find handwritten digits, you could do that classification problem. But if you have a 1,000 by 1,000 image, then, you know, there's a million pixels. And then if you put a million pixels in your second layer, there are 10 to the 12 connections, etc. So you want to analyze this image in a way that's scalable. And this is where the sort of convolution comes in. So the idea is that, well, you want to, for example, pick out the edges, and you want to find things that can be translated in any part of the image. So they're, you know, different motifs. So what is done is, rather than having this general network, you have several sort of convolutions with patterns that can slide around. And what that pattern is something you can vary. And then that creates another layer that may have less resolution. And then there's sort of general layers. And that's sort of a way to make this scalable. And here you can see this sort of library of patterns. And this, I guess the white here is sort of negative and positive. So this is a little like a, you know, Mexican hat wavelet. So this would be something that would, you know, pick up your edges. I guess it would pick up this edge as well. And you see those for different directions. And we can go back to biology. There's actually something like in the eye, there are some layers where there actually is a Mexican hat wavelet hardwired in, so that edges are sort of made to stand out as an intermediate data product. So a convolutional network is sort of putting your general network into a straitjacket, which will, by allowing there to be, you know, say 50 different patterns that you sort of look for and make a simplified image, and then analyze that. Okay, so that is sort of the theory of how the classification problem is dealt with. So there are other things you might want to do. And generative networks is one example. So this this image here is actually not a real person. This is a neural network has been given sort of a library of human faces, and then it can, based on that library, sort of make fake faces out of random noise. So you just take white noise, you put it through this network, and it'll create an image. So, I mean, this is sort of, this is pretty convincing to me, at least. I mean, I would have thought that it was a real photograph. So how would you program this? Well, you have a network that creates fake images through the weights. So it would have a large number of outputs. And then you program another network to discriminate between the true images and the fake images. And that sort of gives you a score, based on some library of human faces. And then that is used to improve the weights of the network that creates the fake images, and then you sort of iterate back and forth. So this is rather a mouthful of jargon: generative adversarial network. So I guess you have the generator and the discriminator, and they're each trying to work against each other, and it's sort of a minimax problem. So there ideas, papers, how to do this, for example, to create galaxies, to fill in foregrounds in CMB maps, etc. We could ask, could you use, say, AstroPH as a training set, and without any human intervention or intelligence, could you write a program that sort of writes fake papers, and then you would train a neural network to try to figure out which papers are fake compared to the large collection of archive papers. And I remember being very amused. There's someone who programmed in a completely different way this Dada engine that'll write social science papers. And there it was sort of based on Chomsky's grammar, so that the computer program, using these different templates and substitutions, would create sentences that look like sentences out of a paper. And then there was a sort of specific grammar that, where you could put famous university, Cambridge, Princeton, Harvard, and it would choose that and put all sorts of things together. And to the non-expert, the papers looked like possible papers. So that's sort of a facetious goal of where one could go, other than just images, also do language. So how well does all of this work? Well, this is a paper that, I mean, if you read the text in these papers, you really don't know what to think. But if you look at some of the images, it's really quite impressive, I think. So in this paper, and I think this is one of these generative adversarial networks that I just explained. I don't really know what contextual attention is, but here they take real images and they mask out part of the image, and then the purpose of the network is to sort of fill in these missing pixels with something that is convincing. So if you look at this natural scene, it seems pretty convincing. You can't really tell what are the regions that have been masked out and that have been painted in. So I guess an artist would be able to do this, or someone with some skill, but here it's just the computer. Or here, sort of continuing a human face. So I guess the network must have learned something about sort of human anatomy and, you know, the size of the eyes and the nose, et cetera, to do this extrapolation. Or here's sort of a fur type texture. And I mean, this would be rather hard to do with sort of conventional computer programming. So I guess, well, I said I would say a little about programming. So there are these Python libraries, Tensor, PyTorch. There's also this TensorFlow that is on the Google cloud. And I mean, a lot of the sort of standard stuff has already been programmed. And as you can see from the sketch, a lot of this is sort of highly, a lot of linear algebra, but it's pretty much the same for all applications. I guess if we look at the classification networks, well, how do you define your loss function? What data do you use? Is there any pre-processing, et cetera? I mean, a lot of this is generic. So, and then there's also special hardware GPUs that can be used to make this a lot faster without specially programming it. And Google has, I don't know, TPUs, tensor processing units. So they've designed special hardware just to do this kind of stuff. But I think Devin has done some programming of this sort, according to Coffee. So, I mean, this is sort of my introduction or summary of what I learned about this subject. So thanks a lot for listening.
Thanks, Martin. Yeah, this was quite interesting. Yeah. Yeah, okay. Does anyone have any questions for Martin?
Is Stefan? Is Stefan on?
Yeah, he is. Yeah.
Yes, I'm here.
So what have you done in this area? He was saying that you've looked at this.
So we've got, there's a few things that we've tried out. So the kind of most obvious thing, I think, with the radio, sorry, there's an echo coming from somewhere.
I think, let me.
Oh, sorry. So one of the things that I think quite a few people have tried in radio astronomy and is a reasonably obvious thing to try is RFI masking. Because you can essentially define that as like a classification task. Scott has been looking at that not really from a like neural network perspective, but more like he's been applying like clustering algorithms to that. But then we had an honors student, Kushen, as well, and currently a master's student, Sola, who's looking at applying like convolutional neural networks to this. There's also a master student, Lisa, in computer science, who's been working on trying to do essentially an autoencoder, which is well, I guess it would be more like a denoising autoencoder style network to try to construct like an optimal foreground filter that works on the visibility space. And I think a few people have looked at using convolutional neural networks to do 21 centimeter foreground filtering in the like map space as well. I know there was at least one poster on that on the most recent Surveyor conference, and I've seen one or two papers on that too. Yeah, so those are the sort of interesting things I think we've looked at. I mean, another thing people have done is FRB searching using convolutional neural networks, which I think is something that it's reasonably well suited to, except that those algorithms tend to have to be working extremely fast on like real-time data. And while neural network codes can be made quite fast and quite computationally efficient, I'm not sure if they quite match the performance of the sort of more bare metal algorithms that are used for that at the moment. Yeah, I don't know if that answers your question. Sorry, I just like waffled on a bit.
Sure. I mean, I was curious.
Yeah. So generally we've used TensorFlow, which is quite useful. And the like Keras API for constructing networks is quite user-friendly. So if anyone's interested in this, I encourage them to take a look at it from that perspective. The one other nice sort of adjacent thing you get from a lot of these libraries is just ways to like automatically compute gradients of functions, which can be useful, outside of these, outside of specific machine learning algorithms. So that's one thing that's quite easy to do with TensorFlow. And there's newer libraries like JAX is a new library out of Google that's good at doing this. And it's also an easy way to get code running on GPUs, for instance. So even if you're not necessarily interested in neural networks, I would say you should probably give some of those libraries a look because they're quite useful for other purposes.
Yeah, that's interesting. I mean, the backpropagation is, it's not that profound, but it probably would be a mess to program on your own and do in a way that's fast.
Yeah, exactly. So, a lot of people have put a lot of effort into like writing up the gradients for a lot of useful functions and allowing them to chain together easily. So yeah, if you need that, it's not a bad thing to take advantage of.
mean, it seems a bit of a mystery how all of this works. For example, with the classification problem. I mean, you're not really interested in representing any function. It's sort of you want to put your functions into a bit of a straitjacket and have some power to extrapolate or to generalize. And I mean, I sort of get the feeling that this has been sort of developed empirically and nobody really knows why it works, or I don't know if
that's my impression as well. Yeah, like, I mean, just there's a lot of simple questions that don't seem to have good answers except from people's intuition. You know, like when you've got a specific problem, some of the questions you might have is, you know, how many layers deep should I build this network for a problem of this scale? And it's like just those kinds of things. Some people seem to know really well, just like they have a sense of this from experience, but there's no like good, even just like rule of thumb solutions for a lot of the simple questions. I'm getting started with this. So yeah, it is very empirical in my experience as well.